Good evening, Lamai. Today we are going to discuss about the gaseous mixtures, gas mixtures, right, and the concept of partial pressures. Right. First of all, let's discuss about the gas mixtures. Right. The best example for a gas mixture is actually the atmospheric air. Right. When it comes to the atmospheric air, you have few components there. N2 gas is there, 78% of the atmospheric air is with N2 gas, and then you have the 21% of oxygen there, right? Some little amount of H2, hydrogen, the CO2, and even the moisture is there, right? So the atmospheric air is the best example for a gaseous mixture. So today we are going to discuss about those gas mixtures, right? So when regarding the gas mixtures, the first concept we are going to study is the concept of partial pressures, right? Concept of partial pressures, right? What this means, what this partial pressure means, right? The concept is like this. Just consider a gaseous mixture like this. So this is my gas mixture, right? Which is composed of, let's say, three gases, three component gases. Gas A, these are the particles of gas A, right? These are the A gas particles, right? And these are some B gas molecules, gas B, right? As well as gas C. The component gas C is also there in this mixture. See, right? This is a gaseous mixture, right? Which is composed of gas A, gas B, and gas C. These A, B, C are referred to as the component gases, gaseous components of the gas mixture, right? So the concept of partial pressure is like this. If you are to think of the pressure exerted by the gas A gas particles, the pressure exerted by the A gas particles on the walls of the container, then it is referred to as the partial pressure of A, right? If you are to think of the pressure exerted by only the A gas particles, the blue color ones, on the walls of the container, that is referred to as the partial pressure of A, right? Partial pressure of A. And it can be symbolized as PA, pressure by the gas component A, pressure by A particles. This is referred to as the partial pressure of A gas in your gas mixture. The pressure exerted by the red colored gas particles, pressure exerted only by the red colored, the B gas particles, is referred to as the partial pressure of B. That is the simple idea, right? So which will be denoted by PB, pressure exerted by only the B particles, B gas molecules. That is referred to as the partial pressure of B gas in your gas mixture. If you think of the pressure exerted on these walls of the container only by the green colored or the C gas particles, that is referred to as the partial pressure of C. Normally symbolized as PC, pressure exerted by C gas particles. Partial pressure of C. So one can say, if you need a definition, simply one can say pressure exerted by gas particles of one single component gas on the walls of the container of the gaseous mixture is referred to as the partial pressure of that component gas in your gaseous mixture. Pressure exerted by a considering gas component on the walls of the container containing the gas mixture is referred to as the partial pressure of that component gas of your gas mixture. Right? That is the definition of the partial pressure. Right? So very simple definition, right? So if you have to think of the total pressure of the system, that should be definitely will be equal to the pressure exerted by the blue colored ones plus the pressure exerted by the red colored ones and plus the pressure exerted by the green colored ones. That summation will give you the total pressure of the system. So one can say, right, the summation, if you take the summation of these three partial pressures, the PA plus PB plus the PC, summation of partial pressures of all the component gases of your gas mixture will be equal to the total pressure of the gas. Right? That is a very simple idea, right? Actually, this relationship is referred to as the Dalton's law of partial pressures. This is referred to as the Dalton's law of partial pressures. Right? Summation of all the partial pressures of all the gas components, summation of partial pressures of all the gas components will be equal to the total pressure of the system. Right? That's referred to as Dalton's law of partial pressures. Right? That is very easy, a simple idea, right? So definitely the total pressure should be the summation of the pressure exerted by the blue gas particles, red gas particles as well as green gas particles, right? So that should give you the total pressure. That is a very simple idea. So that is the concept of partial pressure and the Dalton's law of partial pressures. Right? Okay. So if you have to go through the note, the page number 9 of your note, right, you would come up with a little bit of a different definition for the partial pressure, bit of a different definition than I had explained now. What I have said was actually the pressure exerted by only the molecules of a given gaseous component on the walls of the container is referred to as the partial pressure of that considering gaseous component. That was the definition I have given. But if you have to go through the note, you will see some other definition. Right? Let's read that definition. It says, at your note, it says the pressure that a constituent gas of a gaseous mixture would exert if it alone occupies the volume of the gas mixture at same temperature is defined as the partial pressure. Let's say, so what it says, right? The definition says, right? Another definition says the pressure exerted by a component gas of the gaseous mixture if it alone occupies the total volume of the gas at same temperature. there is another definition, right? Can be written for partial pressure of a gas. Let's try to picturize this idea as well. What I have told earlier is the simplest way of looking at the concept of partial pressures. So this is another definition, the resource book definition, right? Let's try to have a good picture of this definition as well. See what it says, right? It says kind of this, right? This says, right? The point is this, right? Let's say the volume and the temperature of this gaseous mixture is actually V and T, right? This definition says if you are regarding to the partial pressure of A, right? If you are regarding to partial pressure of A, partial pressure of A gas component, it can be picturized like this. It says if only A gas particles are appearing, if only A gas particles are appearing at the total volume of your gas mixture at the same temperature. It's like this kind of scenario. Only the A gas particles are appearing, right? See? Only the A gas things are appearing like this. If only the A gas particles are appearing like this at the same volume as the gaseous mixture at the same temperature, then the pressure exerted on these walls is referred to as the partial pressure of A. Partial pressure of A, right? If only the A gas particles are appearing, no B and C there, right? At the total volume of the gas mixture at the same volume, same temperature, then the pressure exerted on these walls of the container is referred to as the partial pressure of A. This is a very simple concept, Laman, right? Actually, when you are to think of the ideal behavior of these gases, actually, the A guys, the A particles won't feel the presence of the B and C guys, no? The A gas molecules won't feel the presence of other gas molecules in the container, no? If A, B, C are behaving as ideal gases, because the distance between these gas particles are very high compared to the size of them. Assumptions in the ideal gas, right, situation. The distance between the particles are very high compared to their sizes. And no intermolecular attractions or repulsions. No interactions between the particles, among gas particles. Right? So that the blue color ones won't feel the presence of the other gas particles in your system. So that to A gas particles, they feel only those are available in your system. When it comes to A gas particles won't feel the presence of B and C at the container. They behave independently one another, so that A gas particles won't feel the presence of B and C in your container. So that to A gas particles, the container is like this. So that the pressure exerted on the walls of the container here is same as the pressure exerted on the walls of the container by just the A gas particles. Right? So that is the definition. That is the second definition for the partial pressure. If the considering component gas alone occupies the total volume of the gaseous mixture at the same temperature, the pressure exerted on those walls is referred to as the partial pressure of that component gas in your gaseous mixture. That is the idea. If you think of the partial pressure of B, right, it would be like this. When only the B gas particles alone occupies the total volume of the system, right, the pressure exerted on those walls is referred to as the partial pressure of B, right, like this. For the B gas particles, they won't feel the existence of A and C, right? Like this, no? The B gas guys, right? So they won't feel the presence of A and C, right? So the pressure exerted on these walls is referred to as the partial pressure of B. For the C as well, you can think of the same, right? So that is this definition: the partial pressure, the pressure exerted by a component gas of the gaseous mixture if it alone occupies the total volume. If it alone occupies the total volume of the gas mixture, at same temperature, right? So that is the second definition, and this is the resource book definition, right? So I have started up with the simplest idea, right? So you have to have both the ideas about the partial pressures, right? This is in a gaseous mixture, the pressure exerted by only the considering gas on the walls of the mixture is referred to as the partial pressure of that considering gas of the gaseous mixture, right? That is that first definition. And second definition is, if, right, some component gas is alone, right, at the mixture, at the total volume of the gas mixture, right, the pressure exerted by those gas particles is referred to as its partial pressure at the same temperature, right? The same idea, right? Two different pictures, but giving you the same idea about the partial pressures, right? Got the idea? Right. So anyway, the summation of partial pressure should be equal to the total pressure of the system. That is very clear idea. That is referred to as the Dalton's partial pressure law, right? Okay, let's go to the note again, right, at the page number 9. After this partial pressure thing, they had came up with the Dalton's partial pressure law, right? It says the total pressure exerted by the mixture of non-reactive gases is equal to the sum of the partial pressures of individual gases. That is Dalton's partial pressure law. Let's try to derive that thing, right? Let's try to derive the Dalton's partial pressure law, right? Right. So in your second term exam, most of the school's papers are with that question. Derive the Dalton's partial pressure law. That question is, they are with almost all the second term test papers, right? Let's try to derive the Dalton's law of partial pressures, right? Okay, Dalton's law of partial pressures. Partial pressures. We know that. What is that? That is the summation of partial pressures of all the gas components in your gaseous mixture is equal to the total pressure of the system, right? Let's try to derive that thing, right? Okay, so this is the derivation. This is the derivation. right? Let's consider this gas mixture, right? We can write the P equals nRT by considering gas A. Let's consider gas A. For gas A, component gas A, right? This side for A gas. Gas is component A. We can write the P equals nRT like this. When considering the A gas particles, pressure exerted on walls of the container only by the A gas particles is referred to as the PA, partial pressure of A, and the volume of the container is V, volume of the container where the A gas particles move, right, is V, is equal to, let's say the number of moles of A gas particles is Na, R, and temperature felt by the A gas particles is T, right? For gas particle A, component A, you can write the equation like this. For component B, for gaseous component B as well, you can copy that same equation, right? When considering the gaseous component B, the pressure exerted by B gas particles is referred to as the PB, and the volume felt by the B gas particles is actually the volume of the container. These B gas particles feel the total volume of the container, right? And number of moles of B gas particles is in B, R, and temperature felt by the B gas particles, red color particles, is actually T. And V and T are common characteristics. Actually, V and T are characteristic for the vessel, right? V and T are characteristics for the vessel, right? Okay. For gaseous component C, you can come up with PC, the pressure exerted by only the green colored gas particles, right? PC, and the volume felt by the green colored gas particles, volume, that is the total volume of the system, right? Total volume of the vessel, right, is equal to number of moles of C gas particles, R, and the temperature felt by the C gas particles is T, right? So actually we had used the P equals nRT as a component equation here. Here we had used the P equals nRT as some component equations. So P equals nRT for component A, P equals nRT used for component B, P equals nRT used for component C, right? Okay. So for the total mixture, for total gas also we can use the P equals nRT, right? For total system also we can use the P equals nRT. Then it comes as total pressure into the volume of the total gas. The volume felt by all of these gas particles is the volume of the container, right? Is equal to total number of moles of these gas particles Nt, R, and the temperature felt by all those gas molecules is T, right? We can write the equation like that. No, these are component equations for the P equals nRT, and this is the total system equation, right? Okay, from this we can come up with some relationship as Na, relationship for the Na. The Na is equal to, right, PAV over RT. With this one, this gives you a relationship for the NB. NB is equal to PBV over RT. If you substitute the NC here, PCV over RT, and subjecting the NT will give you PTV over RT, right? But we know, right? But we know that the total number of moles of your system, the NT, is equal to number of moles of A plus number of moles of B plus number of moles of C. Right? Just apply these values there. Then you will see NT is PTV over RT is equal to PAV over RT plus PBV over RT plus PCV over RT. Right? So you see V over RT is common, right? So V over RT is common. You can write it like PTV over RT is equal to V over RT is common with this side. Then you get PA plus PB plus PC. So if you have to cancel off these things, V to V and RT to RT, you will get this thing. PT is equal to PA plus PB plus PC. That is the Dalton's law of partial pressures. Right now, total pressure of the system is equal to the summation of partial pressures of all the component gases in your gaseous mixture. Right now, so that is the idea. That is how you are expected to derive the Dalton's law of partial pressures. Right now, just complete the stuff, Lama. Just draw this picture and complete up to there. Right? Okay. Right. So complete, Lama. Here we actually see that we can use the P equals nRT, that ideal gas law, right, as a component equation as well as the total system equation, right? For any component gas of your gaseous mixture, the P equals nRT can be used, right? For the gas component A, it is PAV is equal to NART. For the gas component B, it is PBV is equal to NBRT. For the gaseous component C, it is PCV is equal to NCR. P equals nRT as a component equation. When it comes to this one, it is the P equals nRT as a total system equation, where the total pressure into V is equal to total number of moles into RT, right? So get that idea, so that we can use the P equals nRT with two methods. One is as a component equation, the other method is as a total system equation, right? Okay, right. So you can take a screen capture as well, right? Let's move to the next section, right? Right. This is how to derive the Dalton's law of partial pressures, the first law of partial pressures. Actually, as Dalton's law of partial pressures, there are two relationships. One is this: the total pressure is equal to the summation of partial pressures. That is one way of that is one kind of a relationship referred to as the Dalton's law of partial pressures. There is another relationship referred to as the Dalton's law of partial pressures, which is given as the partial pressure of a component gas is equal to mole fraction of that component gas into total pressure. Such a relationship is also there. Let's discuss what that relationship means and how to derive that thing, right? Now we are leading up to that, right? The second relationship regarding the Dalton's law of partial pressures, right? Let's complete that thing. Right. So at your next page, page number 10, you would see that relationship, the partial pressure, the relationship between the partial pressure of a component gas and its mole fraction as well as the total pressure of the system, right? Let's try to derive that thing, right? So the second relationship, right? Dalton law of partial pressures, the second relationship, right? Actually, that is referred to as the partial pressure of a component gas is equal to its mole fraction and the total pressure of the gas, right? That is the second relationship. Let's try to derive this one. So you should be able to derive both of these relationships, right? Let's come up with the derivation. Of the second relationship, right? Okay, it is very easy, Laman. Again, we can come up with kind of a component equation for the gas component A, let's say. For gas A, we can write the P equals N as a component equation. If you are considering only the A gas particles, we can write the pressure exerted by A gas particles only is PA, and the volume felt by the A gas particles is V. That is equal to number of moles of A gas particles and R, and the temperature felt by A gas particles is actually T, right? We can write like that, no? So if you have to consider the total system, total gas mixture, considering the total system, for total system, one can write the pressure of the total gas mixture, total system is PT, total pressure. The volume felt by all the gas molecules is actually the V, the same volume as the volume of the container. And we can say the total number of moles as the number of moles for the total system, total number of moles appearing, and R, and the temperature felt by all of these gas molecules as the total system is NT, so T, temperature, right? Which is a characteristic for your vessel, right? So if we are to divide this 1 by 2, if you are to divide this 1 by 2, right? If you divide this 1 by 2, what you would observe is actually it's like this, no? PAV divided by, at the left hand side, PTV is equal to, at the right hand side you have NART, at the left hand side NTRT. So you clearly see the V's will cancel off as well as the RT terms. So we'll come up with PA over PT is equal to Na over 8 Nt means the mole fraction of A, number of moles of A divided by the total number of moles, that is mole fraction of A. So this will simplify. If you are to subject the PA, partial pressure of A, that will give you as PA is equal to XA P total. See, right? So the partial pressure of a component gas is equal to its mole fraction at the gaseous mixture into the total pressure of the gas, right? So that is how we are supposed to derive the second relationship appears with the Dalton's law of partial pressures, right? Just complete that stuff as well, right? If you are regarding the gaseous component B, it is going to be partial pressure of B is equal to mole fraction of B into PT. If you are regarding the C gaseous component, it will be PC is equal to XCPT. The partial pressure of C is equal to mole fraction of C into total pressure, right? Like that. Okay. So just derive this stuff as well. Just complete the note. Right. Okay. So that is all about the partial pressures, the two relationships, Dalton's two laws of Dalton, right? So one relationship says the total pressure of the gas mixture is equal to the summation of partial pressures of the all gaseous components. That is the first relationship under the Dalton's law of partial pressures. The second relationship says the partial pressure of a considering gaseous component is equal to its mole fraction and the gaseous mixture into the total pressure of the gas. Right? Those are the two relationships regarding as Dalton's law of partial pressures. Right. Let's use these things. Right? Let's use these terms to solve a simple question. Right? Okay. So there's a question appearing in your page number 10 of your tute. Just try to do that. Just go to the page number 10 in your note. Right. So what are the questions, what are the equations we have learned so far? So basically we have learned the ideal gas law that can be written as a total system equation as well as a component equation. Right? So ideal gas law can be written as a total system equation or as a component equation. Right? What are the other things we had discussed so far? The two Dalton's laws, right? Which are actually partial pressure of gaseous component A is equal to mole fraction of that component into P total. And the fourth form is total pressure law, right? PT is equal to the summation of partial pressures. Right? These are the things what we have learned up to now. The equations, right? These are the tool set we are going to use to solve these problems. Right? Okay. Let's try to do the question. Let's try to do the question appearing there. See what they are saying. Right? What are the things they are saying with this question? It says, right, 2 moles of A gas and 3 moles of B gas was kept in a rigid vessel at 27 Celsius. Right? So the question says you have a rigid vessel, right? So I'll write it in black color, that's better, right? So you have a rigid vessel which contains some A gas as well as B gas. How many moles of them? 0.2 moles of A gas and 0.3 moles of B gas. Those stuff are there. And the temperature of the vessel is referred to as 27 Celsius. Okay. The total pressure of the system was 2 atm. The total pressure is given as 2 atm. Right? What is the first question they are asking? The first question they are asking is the partial pressures of A and B. They are asking us to find the partial pressures of A and B. The two questions they are asking is to find out the PA and PB. Those are the two questions they are asking us to find. Right. can't we come up with the partial pressure here? So basically, let's see what are the tools available to come up with these partial pressures, right? These are the 4 tools, 4 equations we can use, right? So basically, this first equation is not with any partial pressure term, but this equation, because this equation here, this is regarding the partial pressure of A, right? The pressure exerted by only the A gas particles. When you use the Peaker's nRT as a component equation, there also a partial pressure term appears. Pressure exerted by only the A gas particles. That is equal to volume of the vessel into number of moles of A gas particles into RT. Right? Here also partial pressure term appears. Here as well. In this scenario, only 2 components are there, so PC is not there. Right? So we are supposed to use one of these 3 relationships to solve for PA. First of all, let's try to solve for PA, partial pressure of A. Right. If you are to use this relationship to come up with the partial pressure of A, first you need to find all the other terms. You need to know all the other terms appearing with the equation to use this one to find out the PA. But the problem is, even though you know the total pressure, you know the temperature and R and A, even though you know these 3 things, the data provided for these 3 things, R is also known, always known, that is 8.314, right? Even though you know these 3 things, but you don't know about the V. Without knowing the V, you can't use this equation to come up with the PA. So this is not going to be the equation. This is not going to be the tool to use to find out the PA at this instance. Right? You know the T, R is always known, 8.314, and you know the NA, number of moles, but you don't know the V. Without knowing the V, you can't apply this equation to find out the PA. So this is not the tool to use here. What about this one? Do we know these 2 values, right, to come up with this equation to solve this one? The PT is given, the total pressure is given, is known, and the XA is actually NA over N total. XA, the mole fraction of A, is actually moles of A divided by the total number of moles. Actually, those numbers are known. Moles of A is known, 0.2. The total number of moles of the system is 0.2 plus 0.3, that is 0.5. So actually, XA is also known, right? 0.2 over 0.5. So as you know all the other variables, you know about the other variables, you know about all the other variables of this equation, you can use this one to come up with the PA. Yes, so that this is going to be your tool to use to find out the partial pressure of A. Right? Let's use this one then. Right? Okay. So I'll come up with Roman number 1 here. Right? So to come up with PA, I'm going to use the XA P total, Dalton's law. Right? The XA, mole fraction. The XA is the number of moles of A divided by the total number of moles. The number of moles of A is 0.2 divided by the total number of moles. Total number of moles is 0.2 plus this 0.3, that is 0.5. And P total is what? P total is given as 2 atm. So you can apply the pressure in terms of atm here, no worries, right? No need to apply this value in pascals. It is not a must here, because this is not a equation derived from, this is not a equation with the appearance of R, right? This is not a equation with the appearance of R, right? It's not an equation with the R. It is a gas constant. It's not appearing with this equation, right? So that it is not necessary to come up with these units. So you can use the ATM thing as well, right? No worries. For any equation with the appearance of R, you need to come up with the S units, but this is not such, right? So with this, we'll come up with something like, so 4 over 5, that is 8 over 10, that is going to be 0.8 ATM. 0.8 ATM as the partial pressure of A. What about the partial pressure of B? So to come up with the partial pressure of B, right? To come up with the partial pressure of B, actually you can use this one or this one. To come up with the partial pressure of B, again you can use this one, because PB is equal to XBP total. To come up with PB, the XB is known. XB is number of moles of B divided by the total number of moles. Both the values are known, and the P total is also known. So again, you can use the mole fraction into P total thing to come up with the partial pressure of B, or else you can use this Dalton's this relationship as well. As now you know the PA and the P total, as you know these two values, as you have found that, no? As you know these two values, you can use this equation to come up with the PB, right? Okay, so I'll use this one for a change, right? I'll use this one. Even you can use this one as well, right? So PB is equal to, then we're going to Dalton's law, right? PT minus PA. So PA plus PB is equal to PT according to Dalton's law, and if you are subject the PB, it is going to be equal to PT minus PA, right? So PT, total pressure, is referred to as 2 ATM minus PA, that was found as 0.8 ATM, and the value is then given as 1.2 ATM. Right now, that is how you are supposed to find the two partial pressures for the A and B. That is clear, right? Okay, let's move to the next section. Let's move to the next section of the question. See what they are saying. They are saying, then X moles of C gas was added to the above system. So then they are saying, then they have added some X moles of C gas, right? C gas, X moles were added. So now the system looks like this. Now in your system, you have the A gas, B gas, as well as C gas. What are the numbers here? With A gas, still the 0.2 moles are appearing, because you haven't released any of the gases from the vessel. So still the 0.2 moles of A gas is appearing, and the 0.3 moles of B gas is appearing. And now you have added some X moles of C gas as well. So this is going to be X moles. So this is the situation with the vessel after adding the X moles of C gas, right? Okay, and what they are saying. Then X moles of C gas was added to the above system, keeping the temperature constant. So the temperature is still kept at 27 Celsius. That is what they are saying, right? Then, right, the total pressure after the addition of C gas was 4 atm. Total pressure after the addition of C gas was 4 atm. Okay. Then what are the things they are asking? Roman number 2, they are asking is, find out the partial pressure of C gas at final system. So Roman 2, what they are asking is the partial pressure of C gas. The Roman number 2, they are asking the partial pressure of C gas, PC. That is what they are asking. So how to come up with the PC again? Partial pressure of C gas. How to find that? Let's think of our tools available. Can we use this one to come up with the PC? No, this is a total system equation. There is no partial pressure term appearing with this. So if you have to think of this thing, P equals nRT as a component equation, PCV is equal to NCRT. PCV is equal to NCRT as a component equation. P equals nRT as a component equation. So you can't apply this one as well. Why is that? Because if you are supposed to use this one as a component equation, what is the problem there? The problem there is actually, even though you know the T and R, you don't know the N as well. The value of N is also not known. X is given as X moles. We don't know the value there, and we don't know the value of V as well. So this you can't apply this equation to come up with the partial pressure of C, as you don't know about these two terms, right? Can we use this one? Can we use this one? Can we use this one to come up with the PC? These are the things available. Can you use this thing to come up with the PC? Yes. So to use this thing to come up with the PC, first you should know the P total as well as the mole fraction of C. Yes, the total pressure is known. Total pressure is known. That is given as 4 atm. Total pressure is given as 4 atm. That is okay, right? Okay. But do we know the XC? Do we know the XC? To find out the partial pressure of C, before that we should know the mole fraction of C. Do we know that? The mole fraction of C is actually the number of moles of C divided by the total moles, right? The number of moles of C is not known, unknown. It is unknown. It is X moles, that is unknown. So that you don't know this value, even though you don't know this value, you don't know this value. So that you can't apply this equation as well to come up with the PC. Then think of this tool. Can we apply this one to come up with the partial pressure? Right? We can't apply this thing as well, right? Can we apply this one, this Dalton's law to come up with PC? We know the P total given as 4 atm. We know these two values. We know these two values, right? Here, we know those two values. Why is that? Still the A gas and B gas guys are appearing at the same vessel with the same temperature and the volume. See, the two things are appearing at the same temperature at the same volume. These are rigid vessels, right? So at the both systems, right, the A gas 0.2 moles of A gas molecules appearing at a vessel with 27 Celsius and B volume. In this one as well, 0.2 moles of A gas molecules are appearing at 27 Celsius with a V volume, right? So that with both the systems, both the systems are identical to A. Both the systems are identical towards A. Same volume is felt by A molecules, same temperature is felt by A molecules with both systems, and same number of moles are there with A molecules with both systems. So the same pressure should appear. P equals nRT is a 4-variable equation. If 3 variables are not changing in two systems, the 4th variable should also be the same, should not change. If 3 variables are not changing with considering two systems, the 4th variable should also not be changed, right? So that the pressure of A here is same as the pressure of A here, right? So that the pressure of A is referred to as 0.8 at this point, and this point as well you have with the same value. What about the pressure of B? The same thing, same number of B moles appearing here and here. B particles feel the same temperature at the two systems, and B particles feel the same volume at both the systems. So as three variables are not changing for B gas molecules, the fourth variable, the pressure, will also not be changed, right? So that partial pressure of B here as well as here should be the same. So that is 1.2. So we know about these two values as well at this new system, so that we can apply this law of Dalton's law of partial pressures, this one, to come up with the PC. This is the only missing variable of this equation, right? Let's go through this to come up with the partial pressure of C then, right? Okay, so let's apply that, right? So P total is equal to PA plus PB plus PC. So P total is referred to as 4 ATM is equal to PA. PA is 0.8, right? Plus PB is 1.2 plus PC in ATM. So, right, if you simplify this thing, this becomes as 2, right? 2 ATM. When it comes to this side, 4 minus 2 is 2. So PC is actually 2 ATM. PC is 2 ATM. Pressure exerted by only the C gas particles on these walls is actually 2 ATM, the partial pressure of C. Clear, right? Okay, let's come up with the next one. Roman 3. Find the amount in moles of C gas added. Find the amount in moles of C gas added, right? Okay, we are supposed to find the amount in moles. Actually, they are asking you to find out this X moles. Find the amount in moles of C gas added. That is what they are asking, to find out the X moles, right? So what stuff we can use to find out the X moles, right? So we can't use this thing. This is not a component equation. So can we use this one? To use this one, right? We know this value. We know this, but still we don't know the volume of the container to come up with the number of moles here by using this tool. So you can't use this one. So but this one can be used. This one can be used. As now we know the PC and now we know the PT, right? You can come up with the XC by using this thing, and XC, right? Inside the XC, the number of moles of C appears, right? You can use this equation to find out the number of moles of C, right? Because inside this, number of moles of C appears, right? Let's use this one, right? So this is Roman number 3, no? I'm going up with the Roman number 3. So Roman number 3 here, right? So you can use PC is equal to XCP total. PC is given as 2 ATM is equal to XC, the number of moles of C gas, that is X, divided by the total number of moles. The total number of moles is 0.5 plus X. 0.5 plus X. That is what the mole fraction means, no? Number of moles of your considering substance divided by the total number of moles. The considering substance is C, so its number of moles is X moles divided by the total moles. Total moles is 0.5 plus X. And PT is given as 488. Right? So let's come up with a linear form. The linear form gives you like 0.5 into 2 is 1. 1 plus this is 2x will be equal to this 4x. Right? So if you are to come up with this side, is 2x is equal to 1. So x is actually 1 over 2. So x is equal to 1 over 2, that is 0.5. So X is 0.5 moles. X is 0.5 moles. Right now? Right. Final stuff. The fourth thing. Right? What they are saying. The fourth one. Find out the volume of the rigid vessel. Find out the volume of the rigid vessel. Right? Volume of the rigid vessel. So, volume. So, volume is appearing with these two expressions, these two relationships. As we know the total pressure, total number of moles. Now you know the X means total number of moles are known, right? You know the X means total number of moles are known, right? As you know the total pressure, total number of moles, and T as well. 26 Celsius, no? As you know about three variables, you can use this total system equation to come up with the fourth variable, which is V. Or you can use this one. As you know the PC, pressure except by only the C guys, partial pressure of C is known, number of moles of C is known, that is the X value, right? But which we have just found, right? And the temperature is also known. So you know about three variables with this equation as well. So you can use this to come up with the missing piece, the fourth one, volume, right? So one of these equations can be used to calculate the volume of the container, right? Let's use one of those, right? I'll copy this one, right? You can use this one as well, right? I'll copy this one. Anyone, right? Even with the component A, you can use, right? Okay. So let's copy this one and solve for that. You can use this one as well, right? Anyway, right? So this is Roman number 4. So yeah, I'm supposed to write this thing. I write it here, right? I'll erase this one. I wish you had completed this thing, right? So I'll erase this thing. Right, and this is Roman number 4, right? Let's apply to the right C gas component. For C gas, right, you can write the Vickers NRT as PGV is equal to NCRT as a component equation. The pressure is given as 2 atm, but when applying to this thing, we have to come up with the SI units, right? So this is the equation containing R. So for such equations, always the SI unit should be used, right? So 2 atm is the partial pressure of C. That means it's going to be 2 into 2 power 5 pascals. B, that is what we need to find. In C, number of moles of C is referred to as, we just found that value, that was X. So 0.5 moles into RT. What is R? The R value is 8.314 joule per Kelvin per mole. And T is what? The temperature. 27 Celsius means 400 Kelvin. Right now? Okay. So just simplify this stuff, right? So you have some 2 into 10 to the power 5 into V, that's equal to 0.5. So you can apply here the 100 over 12, 8.314. Instead of that, you can come with the 100 over 12, right? And 400 is also appearing, right? Let's simplify this one, these things, right? So you have some 1 here and 4 here, sorry, 3 here, no? Right? Then what else? Is 12, right? Okay. So 10 to the power 5 appearing here, some 4 zeros are there. So with these 4 zeros, right, this 5 cancel off, only 1 10 will be remain there. So if you subject the V, we'll come up with something like 0.5 is there, Under that you have 2 comes there, some 6 is there, that means 3 into 2 is 6, right? And one of the this thing will come there, right? 10 to the power minus 1. This comes to the other side as 10 to the power minus 1, right? We can simplify this thing as 50 into 10 to the power minus 2. This can be written as 50 into 10 to the power minus 2. 50 into 10 to the power minus 2. That means that 10 to the power minus 2 and this thing will be 10 to the power minus 3. 10 to the power minus 2 and that there was 10 to the power minus 1, that is 10 to the power minus 3. So simplifying the stuff, 50 over 6 is actually 8, no? 50 over 6, right? That is 8.33, no? 20 is remaining. For the 20 is 3, no? 10 to the power minus 3. BT cubes. The answer comes in S units, right? The answer comes in S units, right? As long as you are substituting in S units, the answer comes in S units. Things are clear, no? Right? V is equal to 0.5 x NCRT. Oh, sorry, no? This is not 400, sorry. I forgot this thing, no? It is 300, no? Sorry. It's 300, no? So it is going to be 300, no? 27 Celsius, no? Right, so you have some 4 here. Sorry for that, Lamai. Right? So it's like 4, no? So this is 8, no? Sorry for that. 8. So that is just 6. Right? 48 is there, some 2 is there. So for 2 it is 2. Yeah, 6.25. Sorry, that is the value, right? 6.25. Correct, no? This is 300, right? 27 Celsius means 300 Kelvin, right? Correct, no? All right. So that is how we are supposed to solve that question. So the volume is 6.25 into minus 3. So you can come up with this equation as well, right? To find out the V, you can come up with the PTV is equal to TRT as well, right? Because all the other variables is known, right? Or else you can use the P equals NRT for component A as well, component B as well. No worries. I just went to the component C. With all the stuff, you should get the same answer for the V. No worries there, right? Okay, that is how you're supposed to solve this one. Let's complete the stuff now. Let's complete these things, right? The Roman number 2, 3, and 4. Okay. Right. So that is all about the Dalton's law of partial pressures, right? Okay. So two relationships are there as Dalton's law of partial pressures, right? We had just completed a question with the use of those relationships, right? Okay, let's complete the stuff. Right. Let's move to the next section now. Right. Now we are leading up to the page number 11. Right? Page number 11. So there we find a relationship between the mole fraction and the volume fraction of a gaseous mixture. Let's discuss about that thing. Right? The mole fraction and the volume fraction. Right? See. Right? What it says. Right? Regarding gas mixtures. Now we are discussing about some relationship between the mole fraction and the volume fraction. Relationship between mole fraction and volume fraction. Right? See. So in your question papers, right? In your term test papers even, there will be questions like this, right? There will be questions like this. So they will give you some system. They will give you some system, a gaseous mixture. They will give you some gas mixture with some component gases, A gas, maybe with B gas, and they will give you the mole fraction. Sorry, they will give you the volume fraction or the volume percentage, like this. Of say, let's say of gaseous component A as 20%. They will give like this, right? And they will ask you the partial pressure of A providing the total pressure of the mixture, right? They will give you the total pressure of the mixture as well. Let's say it is some 10 atm, and they may ask you the partial pressure of A. These kind of questions will appear in your question papers, right? Let's see how to solve these kind of things, right? What are the things we should know to solve this kind of question, right? This is the usage of what we are now going to learn, the relationship between the mole fraction and the volume fraction, right? Okay. So actually we can solve this one. We can solve this one with the use of this equation, if you know the mole fraction. So we can come up with the PA as PT is provided. If you know the mole fraction, we can use that value there and come up with the PA, the partial pressure of A. Then how to find this value? That is our problem here, problem to address. So how to come up with the mole fraction of this thing, right? Okay. The idea is this. Just keep this question bit away, right? Let's discuss a few more stuff about this relationship. After that, we'll come to this question, right? Okay. So in smaller ages, even in your O levels, you have learned that that 78% of atmospheric air contains N2 gas. You learned that the 78% of the atmospheric air is with N2 gas, and you had learned that 21% of the atmospheric air consists O2 gas. 78% with N2 gas, 21% with O2 gas, and some other gases also there. The rest is coming up with 1%. That is learned. But then the problem arises. This percentage, is this percentage is actually a volume percentage or a mole percentage? 78% of N2 is there by what? 78% by moles or by volume? Is that a percentage represent a mole fraction or mole percentage or a volume percentage? Right? That is kind of a problem. We have to ask. So actually, what kind of percentage is that? Tell me. Is it a mole percentage or a volume percentage? With this topic, we are going to address that. 78% of N2 is there, 21% of O2 is there. Is that percentage representing the mole percentage or the volume percentage? Actually, lamai, it is representing, those percentages are representing both. 78% by volume or 78% by moles, both are correct. Both are correct. So atmospheric air contains 78% of N2 as a mole percentage. Atmospheric air contains 78% of N2 as a volume percentage. Both are true. That is what we are learning here. No need to write specially mention whether it's a mole percentage or a volume percentage, as both are true with that. Right? So when it comes to a gaseous mixture, that is the major thing we need to know. When it comes to a gaseous mixture, the volume fraction or volume percentage is equal to mole fraction or mole percentage. That is what you should know. This is the relationship between the mole fraction and the volume fraction. If you know this relationship, right, you can apply this thing to here to come up with the PA. So they are giving you the volume percentage, means actually they are giving you the mole percentage. This is equal to the mole percentage. This thing is equal to mole percentage. So one can say the mole percentage of A is also 20%. 20%. Or one can say the mole fraction is equal to 20 over 100. 20% means 20 over 100. Right? So if they have given you the volume fraction or the volume percentage, that can be used as the mole fraction. That can be used as a mole fraction. So that in this kind of question, so you can use this mole fraction value. You can use the volume fraction value as mole fraction. Right? So you can use this thing like this into 1080 to come up with the partial pressure of A. That is how we are supposed to solve this one. Right? So this is the relationship you should know. For a gaseous mixture, the volume fraction is equal to the mole fraction. Keep that in mind. No need to derive this thing. You can directly use this thing for a gaseous mixture. The volume fraction is equal to the mole fraction of your mixture. So if the volume fraction data or a volume percentage is given, that can be directly used as the mole percentage or the mole fraction of that considering gaseous component, right? So that you can solve these equations, these problems like this. That is what we are supposed to learn with this section, right? So actually in your note, some derivation is also given, right? Some derivation is also given, how this volume fraction becomes the mole fraction for a gaseous mixture, that is also given, but actually no need of knowing that derivation in your A-levels, right? In your A-level syllabus, that is not expected to derive this thing, but what you should know is this relationship. No derivation needed. You can go to the derivation and see, but that is not essential to know in A-levels, right? Derivation is not essential, but you should know this relationship. This can be directly applied in questions, right? Okay. Right. So let's use this thing in a practical question, right? So if they have asked you to come up with the, right, if they have asked you to come up with the molar weight of atmospheric air, you may need to use this relationship, right? Let's do that thing. So finding out the molar weight. This is also known as the average molar weight, right, of atmospheric air. Let's see how to come up with the molar weight of atmospheric air. So they will provide these things, right? The component gas and the volume fractions will be provided. Right, for the N2 gas, O2 gas, and argon and CO2, the values are given. 78.1% of N2 is there. In terms of O2 is 20.1. 0.9% of argon is there in atmospheric air, and 0.03% of CO2 is also there. Let's use these data to come up with the average molar weight of atmospheric air, right? So actually these volume fractions can be taken as your mole fractions, right? These volume fractions can be taken as your mole fractions, right? Mole percentages, right? See, now let's see how to come up with the molar weight of atmospheric air. Lamai, the molar weight of atmospheric air means, let's come up with the definition, right? The molar weight of atmospheric air. This means mass of 1 mole of gas particles at atmospheric air. That is the idea. Molar weight is actually the mass of 1 mole of particles, no? So when it comes to molar weight of the atmospheric air, that is going to be the mass of 1 mole of gas particles at the atmospheric air, right? That is the definition, right? This is the definition. By definition, you get this. Definition of the molar mass is this, no? Definition of the molar mass is the mass of 1 mole of particles. This is the definition of the molar mass, right? So if you are regarding the molar mass of the atmospheric air, that is the mass of 1 mole of gas particles in your atmospheric air, right? So let's try to come up with this value. The weight of 1 mole of particles of the atmospheric air, right? So if we are to consider 100 moles, if you consider 100 moles of ATM air, atmospheric air, it contains 78.1 moles of N2. It contains 78.1 mole of N2, right? This contains, right, 78.1 moles of N2 and 20.1 mole of O2 plus 0.9 moles of argon plus the 0.03 moles of CO2. This is the composition of the atmospheric air, right? According to this, percentage means the number in 100. The number of moles in 100 moles of the system. The number of moles of consumed substance in 100 moles of the system. That is what this mole percentage means, right? So in 100 moles of the system, you have 78.1 mole of N2, 20.1 mole of O2, 0.9 mole of this thing and this, right? Okay. So when it comes to mass, you can convert this into mass, right? Mass of 100 moles atmospheric air, you can write that is going to be mass of this stuff. So mass of 78.1 mole of N2 is 78.1 moles into its G mole minus 1 value. Moles into its G mole minus 1 value. Its G mole minus 1 value is 28, right? Grams, right? Plus the mass of 20.1 moles of O2 is 20.1 moles into its G mole minus 1 value, it is 32. For this, 0.9 moles into its G mole minus 1 value, which is 40. For this one, 0.03 into its G mole minus 1 value, which is 44. This is the mass of 100 moles of atmospheric air in terms of grams, right? This is grams, right? So what we need is actually 1 mole of mass of 1 mole of atmospheric air. So we have to divide this thing with 100 for mass of 1 mole of ATM air. If you are regarding 1 mole, we have to divide all of this stuff with 100. That means ultimately it will come up as 78.1 into 28. That thing should be divided by 100. We can write the 100 like this. Plus all the things are divided by 100, right? So we can write the 100 with each one. Right now. Right, this is the grams. This is the grams. Right? You can simplify this thing and it will come up as 29. Come up as 29 grams. Right? So this is the mass of 1 mole of gas particles in atmospheric air. So that we can say molar weight is equal to 29 grams divided by 1 mole. Mass of the 1 mole of particles. Mass divided by 1 mole. 1 mole of particles. So 29 g mole minus 1. So the molar weight of atmospheric air gives us 29 g mole minus 1. Right? Okay. That is how we are supposed to find out the average molecular weight of a gaseous mixture. I just use the atmospheric air, but for any kind of gaseous mixture, we can use this technique. Actually, this is very easy, Lamai, right? It's not hard. Ultimately, what we have done is actually we had multiplied our volume fraction or the mole fraction with their g mole minus 1 values and got the summation. For all the gaseous components, what we have done was we had multiplied the volume fraction of the mole fraction with the g mole minus 1 values and got the summation. That will give you the moles, that will give you the mass per 1 mole of particles of the gaseous mixture. That is ultimately your g mole minus 1 value. Right? This is how we are supposed to find out the average molar weight of a gaseous mixture. Average molar weight of a gaseous mixture. Right? Just complete this stuff from. So I will do some other example as well. First of all, just complete this. Actually, that is appearing in your note, no? At the page number 11, at the bottom part, this thing is there, right? So no need of writing this thing. Right? Okay. So if you need another example, see, I'll write another one for this concept. Right? I'll write a very simple problem here. Right? Let's discuss about this kind of question. Right? Let's say a gas mixture contains A gas and B gas with volume percentages of 40% and 60% respectively. Right? And the molecular weights are given. Molar weights are given for A and B. For A, let's say it is 10, and for B, let's say it is 50. and they are asking, right, find out the average molar weight of gaseous mixture. If such a question is asked, so it's very easy to find out this thing, right? The average molar weight, let's take it as m bar average, right, of mixture can be found as, right, 40% of A gas is there. That means 40% means 40 over 100 into its G mole minus 1 value, that is 10, right? This is for A gas, and you have B gas as well. It is 60% into its G mole minus 1 value, it's 50, right? If you take this whole value, this will give you your average molar weight. So we can simplify the stuff. Just take the volume fraction or the mole fraction into its G mole minus 1 value and the summation. That will give you the average molar weight of your mixture. So we can simplify this stuff, right, like this. So you have 4 here, and here it is like 30. So altogether 34 G mole minus 1. That is your average molar weight of this kind of a gaseous mixture. The thing is clear. This is how we are supposed to solve for this kind of thing, right? Okay, let's complete the stuff. So this is the usage of knowing that volume fraction is equal to the mole fraction for a gaseous mixture, right? Without knowing this, without the knowledge, this knowledge, you can't solve for this kind of a thing, right? No? So we had used the volume fraction, volume percentages as the mole percentages here, right? Or the mole fractions here. That was the idea there. Okay, right, let's move to the next section, right? Let's move to the next section, right? So our next section, which is at the page number, which one? Page number 12, is actually the concept of reaction table, right? Let's discuss about that thing. Let's move to that section, the concept of reaction table, right? Okay. So now we are going to discuss about the concept of reaction table, right? Concept of reaction table, right? Okay. Let's try to discuss about this thing. Reaction table concept, right? Just go to the question there, Lama. Just go to the question, the first question appearing at the page number 12. Right? The first part is easy now. First part is not that much, right? You can easily solve the first part, right? See, right, the first section of that thing is question number 1, right? At the page number 12. Right? See, this is this term, right? There is a gaseous mixture containing 0.8 moles of N2 gas. See, you have a gas system containing N2 gas as well as O2 gas. What are the amounts there? The amounts are 0.8 and 0.3. 0.8 of this thing and 0.3 moles of this thing. So a mixture of gas contains 0.8 moles of N2 and 0.3 moles of O2. Calculate the partial pressures of the gas if the total pressure is 180 atm. If the total pressure is 180 atm, total pressure is given as 180 atm. Total pressure is given as 180 atm. The first thing is actually to come up with the partial pressures, right? Come up with the partial pressures. That is easy, no? Now, first let's solve for that. Roman number 1. The partial pressures. So we can easily apply the Dalton's law of partial pressures, right? So the P of N2 is equal to mole fraction into P total. So mole fraction means amount of moles of the constituent substance, which is N2 here, divided by the total moles. 0.8 plus 0.3 is 1.1. Mole fraction into P total. The P total is given as 180. So the value is like 0.8 divided by 1.1. Right? What is the value? Let's quickly come up with that value. Right? It is 0.8 divided by 1.1. That is 0.72. The value is 0.727, like that. So one can write 0.73. So if you need to come up with the O2, the partial pressure of O2 as well, so you can come up with this equation as well, P total minus P N2, as the summation of partial pressure should equal to total pressure, right? For one component it is going to be equal to total pressure minus the partial pressure of the other component, right? So it is PO2 plus PN2. PO2 plus PN2 is equal to P total. Summation of partial pressure is equal to P total. If you are subject the PO2, it is going to be P total minus the PN2, right? So that can be applied now. So the P total is 180 atm minus the partial pressure of N2 is 0.73. So the value will be given as 0.27. Almost 27, right? That is very easy. The first section is easy, not that much. That is not our major consideration here, right? Let's copy the second section, Roman number 2. That is what we are referring to here, right? With the concept of reaction table, right? Let's try to solve the part 2 here, right? Part 2 of the stuff, right? Okay. So let's take this one as part A, right? And this one as part B of the question, right? Right. What they have done. Go to the question again. See what they are saying. When the container is heated and kept at a constant temperature, when the container is heated and kept at a constant temperature, N2 gas is partially reacted with O2 gas to produce NO2 gas, right? What they are saying is actually they have heated this one, right? They have heated this up, right? And came up with this kind of a vessel, right, and heated to a constant temperature. So your temperature here is at a lower value, but temperature here is at a greater value, right? This is what it refers to. No? After heating, you obtain this system, right? And they are saying after the heating, some reaction is to occur, right? Okay. So before the reaction, the system is with only the N2 gas and the O2 gas, right? Just after heating, the situation is this, right? Then the reaction start to occur. Right? Then the reaction start to occur, right? So reaction happens. Partial reaction happens, and you create a new system, right? That is what they are saying, right? So they have heated the system, right? This is the situation after heating, but before the reaction happens. So we can consider it as the initial situation before the reaction at higher temperature. And what they are saying is, keeping the temperature constant, they have achieved the equilibrium system, right? So reaction occurs and a new system is obtained, right? Which is referred to as the equilibrium. Just come up with these simple pictures, right? So keeping the temperature constant, they have achieved this, right? Same temperature, right? If the temperature here is X, here is also X, right? Same temperature, right? Okay. So what kind of reaction happened there? So this is the reaction occurred, right? So N2 gas reacted with O2 gas. It is kind of a partial reaction, they are saying, and produce some NO2 gas, right? So now we are going to study the concept of reaction table, right? Concept of reaction table, right? Let's see how to use the concept of reaction table to solve this kind of question, right? I'm again telling you, you had this system at the beginning and they have increased the temperature. Heated means increase the temperature to come up with a system like this. And this is the situation before the reaction occurs, right? This is the situation after heating, but right, a millisecond before the reaction occurs. After heating, yes, reaction start to occur, but this is the situation a millisecond before the reaction. So they are at that moment 0.8 moles of this thing as well as 0.3 moles of this thing will appear. That is referred to as the initial point. Right? That is referred to as the initial point of system. Right? And this is where you achieve after the reaction. This is where you the system you achieve after the reaction. Right? As this is referred to as a partial reaction, that means not any one of the reactants will completely react. A partial reaction means none of the reactants will completely consume. No limited reagent is there. That is what this sign, the partial reaction, means. So at the end of the reaction, you will find the remaining amount of N2 gas, the remaining amount of O2 gas, none of the reactants will totally consume, right? Those remaining amounts will be found, as well as the so formed amount of NO2 will be also there. So this is the situation with the final system, right? Okay, right. Let's try to come up with the reaction table to find out the things here. What they are saying is what? At the equilibrium, the container has 0.7 moles of N2 gas. 0.7 moles of N2 gas, they are saying. And the partial pressure of N2 gas is 1.4 atm. That is also given. Pn2 is also given as 1.4 atm. Right, no? Right, those are the data given. Right, let's try to build up the reaction table to this problem. Right, okay. So reaction tables are constructed like this. The reaction tables are also known as the ICE tables. Sometimes these is referred to as the ICE table. ICE table means, ICE means ICE table. Initial moles, change moles, and the moles at the end. It can be referred to as the end moles or the equilibrium moles. If you are referring to a double arrow reaction, it is the equilibrium they achieve at the end of the reaction. So E represents the equilibrium moles. If this is a straight arrow reaction, it is the end you achieve at the end of the reaction. So then it is referred to as the end moles. No worries, just E, right? Okay. So now we are supposed to complete this table. If you are able to come up with, if you are able to complete this table, definitely very easily you can come up with the answers. Let's try to complete this table. Right? Okay. So this is not balanced, no? Yeah, some 2 should be there, no? This. Right. Let's complete this one. So Lamai, if you are referring to this reaction table is with few blanks to complete. This reaction table is with 9 blanks to complete. So if you are able to come up with complete these 9 blanks of this reaction table, you are done. You can answer any question easily. Right? Let's try to fill these blanks of the reaction table. Right? What are these blanks actually? Actually, this blank gives you the initial number of moles of N2 gas. Initial number of moles of N2 gas. This blank gives you the initial number of moles of O2 gas. This blank gives you the initial number of moles of NO2 gas. What about this blank? This blank. This blank gives you the end amount of N2 gas, the remaining amount of N2 gas. This blank gives you the number of moles appearing at the end of O2 gas, end amount of O2 gas, number of moles of O2 gas at the end. This blank gives you the number of moles of NO2 gas at the end. Right? What about these 3 values, these 3 points, these 3 boxes? Actually, this is all about the change. Change happens when the reaction occurs. Change happens when the reaction occurs. Right? When the reaction happens, change occurs. Right? Always this change occurs according to the stoichiometry. Always this change occurs according to the stoichiometry. The reactants will consume, products will form. That is what we refer to as a reaction, and those things happen always according to the stoichiometry with the components of the equation. Right? So change step always occurs according to the stoichiometry. Here it is 1 to 2 to 2, that ratio. Right? So change step is always connected to the stoichiometry. Connected to the stoichiometry. Change step of your reaction table is always connected to stoichiometry. Right? Okay, let's fill these blanks. Let's fill these blanks. Right? First, let's fill the values they have provided. First, the 0.8 moles. So 0.8 moles 0.8 moles is actually the value at here. That is the initial number of moles of N2 gas, 0.8. Initial number of moles of O2 gas is actually 0.3. Right? This is 0.8 and this is 0.3. At the beginning, at the initial point, you don't have NO2. You don't have NO2. 0. You don't have NO2 at the beginning. What else? What else? What are the other values they have provided? What are the other data? Yes, they have provided you the number of moles of N2 gas at the equilibrium, 0.7. That is this value. Number of moles of N2 at the end, equilibrium, at the end or at the equilibrium. That is also written. So these are the values they have provided with the question, right? So now with these things, we are supposed to fill the other blanks, fill the table completely, right? Let's fill. So basically, after writing all the given data, after inserting all the given data to the reaction table, right, you are supposed to start filling the table by considering the column, these are the columns, considering the column with only one blank is appearing, with only one blank is appearing. If you consider this column, you are with two blanks. If you consider this column, yes, still two blanks are there. But if you consider this column, only one blank is appearing. Yes, definitely you can fill this blank. Definitely you can fill this blank. How come? See, get this idea. You have started with 0.8 moles. You have started with 0.8 moles. At the end of the reaction, you are with 0.7 moles. That means you have consumed 0.1 moles. You have consumed 0.1 moles. At the beginning, you had 0.8 moles. At the end, you have 0.7 moles. That means 0.1 moles has been reacted. 0.1 moles have been reacted. Reacted. Consumed. That means it is minus. Consumed from system. Reacted. That means consumed from system. So from 0.1 amount, the N2 gas amount decreased as it is consuming. Right? That is why this sign appears, minus, consumption. So after filling one of the values at this row of C change, you can fill the other values as well by concerning the stoichiometry. After filling one of the values of this row, the change row, you can fill the row completely by concerning the stoichiometric values. So reacting 0.1 moles of N2 means 0.2 moles of O2 will also react. The reaction occurs with 1 to 2 ratio. So when you are to react 0.1 mole of N2, 0.2 moles of O2 will react as well. 0.2 moles of O2 reacts, minus, consumes, minus. Always you are supposed to copy these signs, right? Minus sign. 0.2 moles of O2 consumed. 0.1 mole of N2 consumed. Minus is consumed. When 1 mole of this thing reacts with 2 moles of this thing, 2 moles of this thing will produce. So when the N2 and O2 are consuming by the reaction, the NO2 is to produce. So that amount of moles will be added to the system, produced. The amount of NO2 will increase by the reaction. Produce means increase. So amount of things produced, that will be denoted as a plus value. So take the stoichiometry, 1 to 2 to 2 ratio. That means 1 to 2 ratio. So if 0.1 mole of this thing to react, 0.2 moles of this thing should produce. Right? 1 to 2 ratio, 1 to 2 ratio. If 1 is to react, 2 will be produced. If 0.1 is to react, 0.2 will be produced. Clear? Right? So that ultimately you will come up with some values here. So you have started with nothing, 0.2 has been produced by the reaction, so ultimate value is going to be 0.2. You have started with 0.3, you have started with 0.3, 0.2 has been reacted, that means you are ending up with 0.1. Right? So these are the values of your reaction table. You had completely filled the reaction table now. So after filling the reaction table, always get the summation of these three values as the end total. After filling this table, always get the summation of these three values, the values appearing at the E row as the total value. That will be very needed when you are supposed to come up with the partial pressures, basically mole fractions. Right? For the calculate the mole fraction, calculation of the mole fraction, NT value is needed, right? So the summation will give you as 1 mole. Always find that value. Even though they are not asking, just get the summation of the values appearing at the equilibrium or the end row as the total value. Because that is very needed, Laman. Because to come up with the mole fractions, you need the in total values. Right? Okay. So this is your reaction table. And another thing to mention here, so when regarding the reaction table, always all of these values at your reaction table appears with a constant volume and temperature situation. Keep that in mind. With a constant volume and temperature situation. V and T are constant for each and every value of the reaction table. Right? Keep that in mind. Right now? Okay, this is the situation with the reaction table. Now we had completed the reaction table. Now let's use these values of a reaction table, right, to complete the question. Right? Okay. Right. Let's see what they are asking here. Right? With the question, what they are asking is, first they calculate the partial pressures of O2 and N2, then calculate the total pressure. Those are the two things they are asking. Right? Calculate the partial pressures of O2 and NO2, and calculate the total pressure. Right? Actually, I have no need of writing these boxes, right? I just written those to clearly understand the concept, right? Okay. So I'll erase those things, right? So the reaction table is clear now? Right. Now let's use these values to come up with the answers for your question. Right. I'll write the answers here. No? Right. I'll erase these ones, right? So let's come up with the Roman number 2 and the stuff. Calculate the partial pressures of O2 and NO2. Right? Partial pressures of O2 and NO2. So we can use the partial pressure equation. So to come up with the partial pressure of O2, we can use this equation. Right? The XO2 means number of moles of O2 divided by the total number of moles. Right? You can use this equation to come up with the partial pressure of O2. But we have a problem here. What is the problem? Even though we can come up with these two values with the use of reaction table, number of moles of O2 as well as the in total, the two values are appearing here. At the end, number of moles of O2 and the in total, the values are appearing. Right? Even though we know these two values, we don't know about the P total, right? We don't know about the P total. That is not given. That is not given here. Right? So to find out this partial pressure of O2, first we need to come up with the total pressure of system. To come up with the partial pressure of NO2, still we need to first come up with the total pressure. So let's try to solve for that. Let's try a method, or let's think of a method to come up with the partial pressure, to come up with the total pressure of the system. So basically, here they have given you the partial pressure of N2. The partial pressure of N2 is given. So we can use this data. We haven't used this thing so far. So we can use this data, partial pressure of N2, to come up with the P total value. So partial pressure of N2 is given as the mole fraction of N2 into P total, right? So if you know the partial pressure of N2 and the mole fraction of N2, that can be done with the use of these values. As you know the mole fraction of N2 as well as the partial pressure of N2, the equation, the partial pressure is equal to mole fraction into P total, will give you the P total value. With use of this thing, we can come up with the P total value, and that P total of the system can be applied to come up with the partial pressures of these two guys, right? That is our approach here. Let's try to complete the stuff like that, right? Okay, so first thing is actually to come up with the partial pressure, total pressure of the system, right? After that, we can apply that total pressure to come up with the partial pressures of O2 and then NO2, right? So first thing is to find out the total pressure of the system, right? So let's write that thing. Finding out P total. Finding out P total of system. Total pressure of system. For that, we can use the partial pressure law for N2 gas, where the data is provided, right? So let's come up with that. So we know the partial pressure of N2 is equal to mole fraction of N2 into P total. So the partial pressure of N2 is given as 1.4 atm. The N2, mole fraction of N2, is actually number of moles of N2, that is 0.7, divided by total moles, that is 1 moles, into P total. This gives you your P total as 2 atm. This is 1 to 2, no? So your P total will be given as 2 atm. So we had found the P total value. So now we can use this P total to come up with the partial pressures of O2 and NO2 gases, right? So find the partial pressures of other gases. Finding out PO2 and NO2, sorry. Right? Okay. So write it here. Right. See, now we can apply this P total value in this equation. As we know, the PO2 is equal to XO2 into P total. Let's apply the values, right? XO2, mole fraction of O2. That is the number of moles of O2 divided by the total number of moles, 0.1 over 1, right? And the P total is now found as 2 atm. So the value will be given as 0.2 atm. So if you are supposed to come up with the partial pressure of NO2, that will be mole fraction of NO2 into P total. So mole fraction of NO2 is now number of moles of NO2 divided by the total moles, right? So 0.2 is the number of moles of NO2 divided by total moles is 1, right? Into 2 atm. So that value will be given as 0.4 atm, right? No? So that is how we are supposed to complete the question, right? So you clearly see the importance of the reaction table in this kind of problem solving. right? So these values, to copy these values, basically to convert the initial values to the end values, to convert the initial values, number of moles, to number of moles at the end, we actually need the help of the reaction table. So the initial values are provided, and to copy the partial pressures of these stuff, basically you should know the right values at the equilibrium. So that can be done, that conversion can be done only via a reaction table, right? Okay. And a very important thing to note that is all the reaction tables are constructed for a constant volume and temperature. You can't construct the reaction table right to this point and this point, because the temperature is changing, right? Always the three stages of the reaction table, initial, change and the equilibrium, should appear with the same temperature and same volume, right? So the reaction table, our reaction table concepts is used here, right, from this thing onwards, right? That is how we are supposed to use the reaction table. Always the temperature and the volume should keep constant throughout the reaction table, throughout the values of the reaction table. All the values of the reaction table appears with the same volume and temperature. That is very needed, right? So this is how we are supposed to use this kind of a reaction table to complete your problems, right? Okay, right. So this is the question number 1 appearing with your note. Okay, right. So few more questions are there, right? Question number 2, 3 and 4, few more questions are there with your note, right? You can do those things at your home, right? I'll provide you the video lessons of those descriptions, so of those explanations of those questions, and first try to solve those things, right, from your own, right? Then I'll provide you some videos of explanations, right? Just complete this stuff, and that's all for today. Then goodbye, Lamai. We'll meet with the next class next week. Goodbye then.